charge button is the pointer. Forward and backward.
Forward and backward, yes.
Okay.
So thank you all very much, and thank Professor Paulo to invite me to be here. And I came for November conference. Some of you I have already met. 3 days conference with a very good exchange of information and getting knowing people, and really hopefully we can work more together, even more together. So I'm, as you said, I'm Ying Guo. I work at NORCE. I have experiences from research in the laboratories as well as in industry and resource modeling or CCS. So, you know, when you grow old, you have more and more experiences in a way. So, but I feel very lucky to be in the industry to work on these very interesting topics. But gradually, when you know the industry better and better, you think, what is my role to contribute to the future, which is sustainable oil and gas industry, in addition with renewable energies, with low emissions and combat the climate change, preserve the environment, diversity. We heard about that yesterday, which is quite new. So nature is as well important as oil and gas industry, right? I'm also thinking what we do has a social impact, no matter what we contribute. And sometimes when you work in your own bubble of your subject, you tend not to think about consequence or impact around you. Oil companies, they have their own economic constraints, economic requirements. Sometimes we actually do best as we can, but maybe it's not best to others, right? It's cheap for you or beneficial for you, you make a lot of money and competitive, whatever, making you rich, but maybe there will be other people suffering or other things, environment suffering. So that made me to be interested in life cycle assessment or analysis, whatever we call it. In fact, this is also something very new for everybody, for the industry, but also for scientific communities, because it's an interdisciplinary subject. So I like to discuss with you what I've learned, and maybe you can reflect what you can contribute in these areas, because this is upcoming areas. The industry will be required to do the whole value chain assessment of your business. So the title I have today is Energy Management Toward a Net Zero Greenhouse Gas Emission for the Oil and Gas Industry on the Norwegian Continental Shelf. But I think the methodology is general, but I'll give some examples which is relevant for the Norwegian Continental Shelf. Paulo, can you, or may Isaac, help me with the timing? Let me know if there are 10, 15 minutes left. I can speed up. Thank you. So I have prepared some slides with the 3 topics. One is about life cycle assessment. Who of you who have been working on these areas or been involved in this? Maybe raise your hand. Not very much. I started with this 2 years back, or maybe more than, maybe the first encounter is during the COVID time. I took actually a small course, which made me very interested. So I'm also very new. So I don't have very much something for you to use or more discussion how we should do that, yeah? But the introduction will be good. And then related to our work, which is, I call it the LCA framework for water management. I'll explain you how we think and how we think it will work in this environment and why we select this environment to test the LCA methodology. The third one is energy management for oil and gas production. That is upcoming area, I would say. Normally we say enhanced oil recovery. LRAP is Oil Recovery Lab, isn't it? EOR. I've been working with EOR for many years. EOR is part of the whole operation. So that's why now, earlier it's like, okay, we increase oil recovery. But then now we have to think, at what cost, right? At what cost in terms of both monetary cost and maybe MPV increase, but also cost in terms of CO2 emission or greenhouse gas emission, and also environment impact. That's why LCA could be a very nice tool to help us select the best method. So, introduction about LCA. I'm not going to teach you because I'm not the right one to do that, neither. But LCA, life cycle assessment, I would say it's quite a natural way to think. It's to see the whole value chain, right? But there is it's actually a very, very distinct scientific discipline. So there are professionals working on that, right? So we have to acknowledge this is not something you can do it by yourself. So the disciplines say, first we have this strict 4 steps. It's what you want to do, why you do it, yeah? And then you have to have a sort of life cycle inventory. I'll explain what it's, it means. Then we have to analyze the impact analysis and the interpretation of your result. So these are the high-level 4 steps. So the step 1 is define your goal. So you have to say what you have to think about where you are going to do this analysis, why you do it, and what is the boundary. That's very important. What is a boundary? You cannot analyze the whole chain, which is maybe not relevant for you, at least not relevant for what I'm doing. And then we have to see the impact categories, where what I want to do impact, in which directions and which areas. And we have to define the function units, meaning that you will end up with some kind of unit to compare with other methods. It could be barrel produced or electricity produced. It could be a T-shirt. This is a type of unit. So one example of the impact category is, it's a long list. This is a list of the LCA professional categories in a way, covering all sorts of aspects. I've been working on these 2 areas, which is environmental cost indicator, that's monetary, and is a global warming potential. We can select some others which are relevant for your goal and your scope in order to compare different scenarios. So you see the cycle. This is a cycle. So we can start from a resource, producing coal, whatever, ore for aluminum. So resource, and then you process, you do the manufacturing of your product, and you distribute to the customers, right, and you use it, and then it's end of the life. But we should struggle more and more, instead of throw it away, either to mountains or oceans and like garbage mountains, very big. We should see how that can be used as resources now in the circular economy. So that's the whole cycle. Then once you have identified your goal and your need for producing something, we have to define and find. So this is a material you will need and so on. But we need to see the inventory. That is to collect all the things you will need to do your work, to produce your product. It could be more raw materials, processing, and raw materials, processing, and the whole thing. And, every step you need raw materials. You probably need energy, whatever, and you get your final product, and you get your waste. And each of the steps you have to identify in detail. So this is the heavy work start. It is like illustrated with the example here. What is the inventory of making a T-shirt with cotton in this particular case? Yeah. So you have to say, well, I have to grow cotton, of course. I have to have some kind of bleach for different colors of materials, and we have to have some different things to produce and all the details, and what will I need in terms of electricity or in terms of water and all that. You identify each of the needs you have. That's the inventory. Then the next step is to do impact assessment, meaning that if I need one, I don't know, certain weight of cotton for my T-shirt, what will that mean for my assessment parameters? In my case, in this particular case, it's a CO2 emission. So we look at, that's not my example, that's a textbook example. Yeah. So if we look at the emission, you have each of the items similar to the previous step to see, yes, bleaching will cost you 4.53 kilo of CO2. So that's the value we'll use in the future. So each of the items will have this associated value for CO2 emission due to the production, due to whatever the methodology you use. So this inventory, you add up, you will end up with the total. Global warming, which is, remember the second item, is 4.85 kilo of CO2 per T-shirt. So that's the way for the LCA analysis. Okay? So, and then you interpret in your own way. You can use it for your own purposes. You identify the significant issues. You identify if the data is accurate and the problems with the measurements, analysis, evaluate your study, and in terms of consistency and completeness, and draw the conclusions. So when you, for instance, compare with another case, you produce a T-shirt with synthetics material. Then you get different value to make you be able to select what you want to have, right? So that's the meaning of or use of LCA. So I find this very interesting for our industry. Oh, by the way, so the previous example is a quantitative measurement of CO2. That's where we have this boundary thing. So the T-shirt, we started with the cotton, but maybe it's not the very beginning. It could also be develop the land and so on, right? So you have to put the boundary. So the boundary you put, the more further out, the more you're close to the cradle, the birth of the process. And then you go all the way to the grave, sorry. This to the, where is my laser? Yeah. So the whole process, every process you have waste and waste and waste, and sometimes you can reuse and recycle and so on. So this is one of the ways to think about ecological loop for the environmental assessment. So there is an example I can show you. It's published in a paper about CO2 EOR for oil production. So our goal then, following the different steps of LCA, is to see the CO2 EOR process related to greenhouse gas emission in the production. And we define the functional unit as a kilo CO2 equivalent per cubic meter of incremental oil. And the system boundary you can define depending on how far you want to go. In this particular case, they claim they have a cradle to grave system, but I sort of disagree because to me it's maybe more narrow than cradle. Cradle is actually in the very beginning, right? So, but you can define yourselves. And then it's the access of CO2 capture rate and net CO2 utilization values and all that. So that's the purpose of that example. So when you see the beginning of this study, that's why I say it's not a cradle. It starts with, say, you have a coal-fired mining process and transport the coal, and you produce electricity without CO2 capture, and you generate electricity. And then this CO2 is captured, and CO2 is going to be used for EOR, right? So we transport the CO2 to the site with a certain cost. So these are the inventory we're talking about. We have to put a value on each of the steps. And we got into operation. So here, we call it gate-to-gate. Actually, this is of our most interest areas, which is what we have control of. It's the operation of CO2 injection, right? And production and so on. So this is what I'm focusing on as well, gate-to-gate. And then we produce oil. We transport to refinery. We have this production of CO2, oil, incremental oil. And what is the emission from this product? So this is one, I would say, a scope of the analysis. You can call it whatever. But I think the most thing we have to relate it to, which is very near our sphere, is gate-to-gate EOR operations. Independent on these values, which are picked from the figures, I think these values will change. It's not a standard. In a LCA discipline, there are databases of standard values. So like how much water we use for cotton production is a standard value. So there are databases to pick these values, and I think we're obliged to use it so that we can compare case by case with different scenarios. But in our industry, oil and gas, I think there are, at least I have not found very agreed values. I think it's not possible. It's very many different scenarios from different places, different locations, different type of field. And so it's not possible. That's why these values are not necessarily relevant for other cases, but for this paper, they picked these values. It's a US paper, by the way. So their goal is to run this process and compare with the different situations. In their paper, they say, okay, I have done my study with this methodology. I arrived to certain, 71 or 57, whatever CO2 equivalent per cubic meter of incremental EOR oil. Then they compare this with other way of producing. So, and they put a ratio of this with the US domestic, which is here. So it's 1 here. And if it's less than 1, it's better. It's performing better, right? If it's bigger than 1, larger than 1, it's worse. So in this paper's conclusion is that the CO2 EOR, case A and B, both perform better in terms of CO2 emitted per cubic meter of oil. So this is a very nice example of using LCA for study your cases, I find. So based on this example and based on what we learn from LCA principles, I would say, we have tried to put up a LCA framework for water management. So the logic of using water management as a case is that on the Norwegian Continental Shelf, we produce more and more water, which probably is similar for all the oil fields, right? There are always water, and at the end of the life, you produce more and more water. We have cases, fields produce maybe 99.9% of water, but still a lot of oil in time. I don't know, Paolo, by the way, do you know the pre-salt water cut now or in the beginning?
Saltwater cut?
Yeah, in general?
I'm not sure, but maybe you can help me with that.
Yeah. How?
Less than 10%.
Less than 10%. So yeah, in the very beginning, yes, that's very good. Anyway, so on the Norwegian Continental Shelf, you can see this is numbers from 2000 till now. The red bar is oil production, and you compare with the orange bar, which is a water production. So in the beginning, at that time, I think the peak is about here. Yeah, maybe, yeah, the peak probably is before 2000. Anyway, so you see the oil production, oil production is bigger than water production. So it's less than 50% the water cut. At the same time, we inject a lot of water to keep the energy of the reservoir. And that's actually in Norway and the Norwegian Continental Shelf a regulatory issue. It's not an issue, regulatory, a mandatory thing you have to do because you're taking out energy from the reservoir. You have to replace that with water to keep the energy. So by law, it has to be done. So we call it voidage replacement. So, and the operating company must report their, luckily many fields are not necessarily injecting water because water aquifer, many fields has aquifer to support. But if you lack of aquifer, you have to replace with injected water. So there are a lot of water, most of the fields are supported with injection water. And you see the injection of water, of course, following the activities and production trend. But you see, at some point, it's switched. We produce more water than injected water. And now we are in the trend in the last 4 or 5 years, we inject more water than water production. So there are a lot of reasons behind these numbers. But in general, we produce 2 times more oil. No, 2 times water than oil. So 60-70% to water, and yeah, so water cut is about 60% in average, but a lot of wells are producing quite a large percentage of water. Compensated by green fields, which is like Johan Sverdrup field, beautiful field. They started to produce maybe 2-5%, so still very good. Yeah, so we are lucky with that. But if you look at the field operation, water injection here, pumping water injection represent 12% of the energy spending on the platforms. That's energy, not necessarily gas to produce energy, because a lot of the energy is actually coming from the electricity. But that's why I think we should think about energy, megawatt, whatever, instead of tons of gas used for energy production. Yeah, energy is important now. The rest of, not the rest, but the big chunk of energy spending are compressions. But compression is everything. We need to compress gas, and we need to, for different purposes. It could be gas lift, gas injection. But from the Norwegian Continental Shelf, we spend a lot of gas to compress gas. No, we spend a lot of compression energy to export our gas to continental Europe. Maybe you saw yesterday, I don't have this figure now, we have a lot of gas pipelines from fields to transport gas to Europe. And compression of gas is energy intensive. So many fields spend probably about half of the energy to export gas to, so these are the main energy users, I would say. Of course, there are other things, pumping seawater lift and for cooling purposes and other purposes for energy, which is, we call it the base load. We have to spend energy for the operation. So we're looking into this, how we can reduce spending of water injection energy. That's one area, because we cannot do very much on gas export. We have to export anyway. Compression is there, so it's a given. So water diversion, I think you also probably work on that, but we work a lot of water diversion, meaning that for the wells we inject, we want to prevent them coming back to the producers quickly. Yeah, we want to prevent them so they stay longer in the reservoir and they can display the remaining oil in the reservoir. I'm not sure. I don't know if your lab is working on this type of technologies. In principle, is it to put a chemical plug into the highway, yeah? So the cars will go around, or the car means water, to sweep the unswept areas. So I bring this case, which is a very nice case for a scientific study. I remember this case was identified not through LCA analysis, but through the different constraints in North Sea. We have to have environmentally acceptable chemicals, and right. So why not the polymer? Well, in Norwegian part of the fields, different from UK, polymer is not allowed to use. Synthetic polymer, sorry, yeah, polyacrylamide, because they are not degradable, which is a conflict with our intention, which is to have a stable polymer, let it stay, and improve the sweep efficiency. But we cannot use it. So at that time, they select the silicate, which is an environmentally acceptable chemical, and they can be used for making this plug, because chemically it changes property or viscosity when temperature increases with the right recipe of this silicate solution. So it was selected to test if it will work for the North Sea situations. Unfortunately, this technology is not pushed to a wider use. So still, we remain with this case, which was done 2011, maybe sometime, I can't remember, a while ago. But it's never applied for a larger field. This is only on one well pair. But we use that for our study in different, different situations. In this particular situation, the injection is around 2000, this time. And afterwards, the well pair has been monitored for different performance. So there are 5 years of production history afterwards. Of course, we have the history before as well, right? So we have used this case to tune our model to say, well, now we can study, if you didn't have this plug injection, what will happen? The well pair already, the producer produced already 98 something water percentage. So after 5 years monitoring, these are the, by the way, I missed the vertical text of the axis. This is water cut. So we try to history match the water cut of the 5 years after the injection, yes? So we know the effect of the silicate plug. And we also simulate, if we didn't do that, if we continue with water injection, which is a blue case, the water will continue like this, injected. But after the plug with silicate solution placed to block the highway, the water injection is reduced. It doesn't mean that it's reduced. It's reduced because the plug increased the injection pressure, which is intended, right? Because the pressure going through the highway is much lower. So with the higher pressure, we can sweep larger areas, but with less water. So the result will be same, and the water cut has been kept low. So that's also another evidence. It results in less water production. But by the way, water production is not spending very much energy. So we didn't even account for this because it's energy from the reservoir, right? So the significant saving of energy is actually on saved injection water. During the 5 years after the injection treatment, we saved about 1 million cubic of water, which is significant. So these are the numbers we put approximately, yeah? By the way, there is also an increase in oil production as compared to if we didn't do the treatment. About For 100,000 cubic, it's a lot. But this field produced much, much more. So the chemical solution with this sodium silicate is a density. It's a little bit dense, well, a lot of dense than water, but viscosity is very similar to water, giving us a possibility to inject without using too much energy. That's positive. And CO2 footprint for this is actually for the chemical itself. How much the footprint for the healing and curing of this chemical. So the total energy, emission from this thing is about this, not thing, it's actually a big quantity. It's about 1.2 tons of CO2 per ton of the total, because we used how many tons of, I can't remember, 1.4 ton. 10,000 tons of this chemical and dissolved in seawater with 4% sodium silicate. Yeah. So, so it's 12 tons of CO2 due to this operation, and total water reduced 1 million, and total energy saved to inject this water is about 20 gigaton. No, gigawatt. All this gigawatts hour of energy. So you see the point. The methodology is to find the way to save energy. At the same time, we know there will be emission. So now you can imagine how the emission will come out for this particular case as compared to the gain. Yeah. So we put this framework, I would call it, to study this this particular project. So the framework. The blue part is what I call gate-to-gate, which is something happening on the platform. It consists of a production, of course, but also all the energy producing units and energy spending units. Also including water treatment. Yeah, water, you can do the re-injection and treatment of intake water in order to do the injection and so on. It's also possible to import electricity in addition, instead of energy from turbines. So that's another associated, how should I say, inventory, I would say. Remember inventory? So my boundary is put here. I don't care about if energy comes from a coal-fired but in Norway, this energy comes from hydropower, which is very low CO2 footprint. But if this energy comes from Germany, because we do import electricity from Germany, I need to account the CO2 footprint of this electricity. So the dirty electricity needs to, be treated differently as clean electricity. Similar with the need for IOR chemicals, additives, which is in our case silicate. We have to find the chemical supply, what is the footprint for that, and the transport of that. Because transport to offshore will take a lot of energy. And this particular place, the chemical comes from Central Europe. So we have to transport a huge amount, 10,000 tons of chemical with many trucks to the shore, close to the supply base, and with ship to transport to the injection point and do the injection. So that's a lot of energy. Yeah. So we have done a certain, remember now, LCI inventory, 10 minutes, yes. So we have different footprints. These are very approximate. So we can say, yeah, we have saved 5 years water injection, and we save about 7 kilotons of CO2, and we have energy saved, and we have incremental oil. We have, now the boundary comes into play, yeah? We have, for this incremental oil, do we count for 3,000 gigawatt hour of energy, which is a benefit? Of course we should, but this energy is spent to burn the oil, or is created by burning the oil, which is not our business. It's exported to the end users. So the boundaries start to blur. We have also footprint for this chemical supply, right? Hello, where are you? Oh, it's gone. So you see different parts of the inventory to add up, which gives us the total, like the previous example, the total cost in terms of emission and CO2 emission. But from gate to gate, we didn't study because at that time we didn't have, this study was done last year, we didn't have this calculator eCalc, which I'm going to explain a little bit more. So we cannot really calculate very precisely the energy spending due to this operation before and afterwards. But what we have done is to say, we continue this methodology to say, if we don't use silicate, but we use polymer, which is another method we're studying quite a lot. It's a polymer that we inject into this, similar with silicate, but we have to inject a larger quantity because silicate is more efficient. So instead of 3 months injection, this inject about 22 months, no, 52 months of injection. So we did a lot of simulations to see how it performs in terms of concentration of polymer and different cases. And then we compare, each of the bars is a simulated case where we have incremental oil in blue and saved water injection in orange. And we pick one of the cases and we study, the total cost, total performance, I would say. So here it's given by energy. So for the silicate case, remember we have a 20 gigawatt hour energy saved. For the polymer case, we have a 12 gigawatt energy saved in the whole value chain after this calculation. So it's a little bit different scenarios. Now we can compare, right, these two cases. So this is idea. So about energy management, which is surfacing now, instead of thinking about money or emission, we have to think about optimization of the energy spending, because energy is money. Energy is also emission because if you use the gas turbines. So we started to test the eCalc calculator, I would say. What is eCalc? It's a software tool to calculate energy demand and greenhouse emission from oil and gas production and processing. Remember, production and processing. So there's two things combined. So how? It's actually by integrating data and knowledge and future plans from different disciplines at different places, surface and subsurface. And it's given the models relating production rates and pressure in the reservoir to required processing energy and resulting emissions. So this is a tool that is very suitable for doing the gate-to-gate analysis of energy. So this is open source. I hope some of you interested in programming and so on, go to this GitHub. It's open source, and it explains the methodology, how to calculate, and it has a very limited documentation because it's quite new. And go and find out if there's something you like to use, open source. What we plan to do is to integrate that in an optimization code so we can optimize what should be used. The main idea is to describe your surface facility in eCalc. To say, well, you have all these turbines, green, generator of electricity, and the electricity supplies energy to compressors and pumps and all that. And you have fuel, you have the fuel to supply these turbines, and you have the flare, which is part of the process. This cannot be avoided, So all that form the calculation basis for the emission of CO2. The speciality is that the research environment, the researchers now is put a lot of emphasis now in energy. But normally they calculate energy with just a very simple calculation to say, I lift this water, I need maybe 1 gigawatt per ton. But it's not that simple because these turbines and pumps and compressors are not linearly related to the energy need. For instance, turbine efficiency is if you have a load of or a production of 15 megawatt, you have efficiency of a little bit 30%, and you increase, you get a higher efficiency. But if you go down, you get a less efficiency. It could be that, you have saved water, but your turbine has to run in low efficiency, right? But it doesn't save fuel. So it's not linear. And this is relationship with the turbine, energy output and fuel, which is almost linear. But the efficiency is not linear. Similarly with the compression, it's not linear neither. The screens, it's like you have a optimal operating window, which is you want to do. You don't want to go outside, step out, and then you get a much less efficiency. So that's eCalc is making sure operation is happening at the best, efficiency. And then you give the input of your production profiles from resource simulation or from a history. What we want to do is to say, okay, we history match the history. We know how this performs, and we forecast the future. What is the energy need, and can we reduce that? Can we phase in other energy source, for instance, or renewable energy source? So, but the trouble now is that we have this division between subsurface people, process engineers, with the subsurface people. We don't talk very much each other, understanding each other. So normally reservoir engineer to say, you have to produce this, and the surface people try to do the best, but maybe it's not the optimal solution. So eCalc could help combining these two disciplines. And Equinor is now training all the reservoir engineers to use eCalc, so they get better understanding. So I think that's a very good approach. So this is what we have done so far. We started using this software this summer with some students. So they have looked into the calculations. So this is a synthetic case where we say, yes, you have this, remember the turbine setup and so on. And we can calculate the CO2 emissions and energy use. And energy use is split it into different, each of the consumers of energy, pumps and compressors and so on. So I think that's a very nice way. So we have run different cases just to check out the capability of the software. And you see we have different cases. We reduce water injection. We can have a different pump discharge pressure, which reflects the reservoir pressure and so on. And we try to compare each of the cases to see where is the energy and emission make differences for different methodologies. So this is where we are now. And the eCalc is not perfect yet, so there are a lot of things they have not programmed into how to, reflect the changes in the operation. So we are collaborating with Equinor to make it more and more applicable. So this is one of the last slides. Is how do we use LCA framework for energy management? I hope we can do more work to describe all these boxes in this framework. It could be different framework as well, but this is a test example. To do the LCI, remember LCI? Life Cycle Inventory. We need to collect all the data and create a methodology and database. And this database can also support the environmental impact, which is not necessarily CO2, but also footprint of toxic elements and footprint of the, of the facility. If you put a water treatment plant, it's another footprint. So we can calculate these things on each of the inventory and add them up, and we do the different scenarios, like a silicate versus polymer versus maybe smart water versus whatever. So we can have a comparison of different scenarios based on the whole sort of value chain in our, not the whole value chain, but in our case, a boundary in this environment. With eCalc, we can do much better the surface performance. Last slide. So reward and challenges. I have already mentioned a lot of that. So I think the really heavy work is to have data from the field, not just production data, but also performance of turbines, emissions, and so on. The industry are now doing more and more monitoring on the CO2 emissions at the chimneys at different spots. I think that will help to give more inventory data, more precise. So I think I'll end here. And more 5 minutes. Okay, for questions, yeah, I think that's good. I just want to thank our sponsors for this work, which is part of the NCS 2030, our research center. Paulo, you know it very well, yeah? This center started 2022, and we are continuing to 2029 and maybe 2030. That's the window of opportunities we can collaborate. You're welcome to join us. It's much bigger than this topic. Yeah? It's all the way from exploration to production to social scientists to education, mobility with students and so on. So there are a lot of opportunities. So hopefully we can continue discussion. Yeah. Okay, I end here and yeah.
Thank you very much, Ying. Thank you for the brilliant presentation. Very interesting. So we have some minutes for questions and comments and curiosities. So I will start myself, just to break the ice. And you showed the graph where you presented water injection and chemical injection in the Snorre field. Mm-hmm. And the objective was to reduce CO2 emissions, of course, or to save energy, of course, reduce the CO2 emissions. But according to life cycle, should we, well, just a little bit back. Yeah. But these also will lead to an increase in oil production, right?
Not decrease, increase oil production.
Huh?
Increase oil production.
Increase,
yes.
yeah, an increase in oil, yes. in oil production.
Yes. Yes.
So according to the life cycle, should we take into account the potential for this increased oil production in generating CO2 as well? So how do we take into account? How does it fits in the scenario?
So the oil and gas companies, they divide CO2 emission into 3 scopes. Scope 1, Scope 2, and Scope 3. Mm-hmm. 1 is what's happening gate to gate, remember, on the platforms to produce. Scope 2 is services that I need to do the job. Yeah. Typically, it could be the chemical producers. Their emissions is Scope 2, but it's included in this inventory. Scope 3 is not. The companies say Scope 3 should be handled by the end users. We sell you the product, you handle the emission. So your question is, yes, it's not included here. Mm-hmm. But if we include it here, we have to include Scope 3 for other scenarios as well, okay. Right? Yeah. So it's a choice. It's a choice, yes.
Thank you. Thank you so much. Mm-hmm. Felipe?
Is ECOL somehow integrated with some platform for uncertainty estimation or measurement? Because you said data is really uncertain for some of the estimations.
Yeah, yeah. Yes and no. It's quite a new ECOL, right? In this center we have integrated uncertainties, geological uncertainties, and also measurement uncertainties into our optimization routines. But it's not through ECalc. It's the simplified calculation I was mentioning to you, roughly per unit this energy and emission. So it's not good enough. It's not optimizing the surface part with this complicated efficiency curve. That's the goal. It's a very good. That's what really I think we should be doing now. So you can help us. You can help us. You have a golden opportunity. Yes.
Okay. We are transmitting this lecture online through YouTube. So if you're online and if you have questions, you can post in the chat and we will read it to the audience here. So more questions, comments, please. Don't be shy. It's a good time for discussions. Come on, guys. No curiosities, no questions. Vocês também podem fazer a pergunta em português, se vocês se sentirem mais à vontade, e a gente transmite aqui em inglês para a doutora Ying. Tá? Ok, deixa eu ver se nós temos alguma coisa.
Yeah. I'll be around in the lunchtime, so we can discuss face by face as well.
Já é 10h30, então nós estamos aqui no nosso horário. Nós vamos fazer um break de 15 minutos para o coffee break e nós retornamos 15 para as 11 com a palestra do professor Ingebret Fjeld. Tá? Então vamos dar um break de 15 minutos para o coffee break e retornamos aqui 15 para as 11. Ok? Muito obrigado a todos. E o coffee break vai ser servido aqui na tenda, bem aqui ao lado. Tá? Muito obrigado a todos. E, mais uma vez, uma salva de palmas para a doutora Ying, por favor. Muito obrigado.